Let's discuss the properties of radicals. So the first property you'll see is the product property, and it says that the nth root of a product AB is equal to the product of the nth roots. So if we take the nth root of AB, that's equal to the nth root of A times the nth root of B. Now the second property is called the quotient property, and it says that the nth root of a quotient A over B is equal to the quotient of the nth roots. So we have the nth root of A over B, and that's equal to the nth root of A over the nth root of B. Now the last thing that I want to talk about is how to get a radical in simplified form. So for instance, you're working through a problem and you come up with an answer, and it's the square root of 4. So if we look at this radical here, now is this radical in simplified form? It isn't, because the factors of the radicand, which is 4 here, so we have this is equal to 2 squared under our radical sign. So these factors here, this factor, the power for that factor, can't be equal to or greater than the index of this radical sign. So essentially the index of this radical sign here is 2. So we have an equality here. So we need to make sure that we simplify this radical even further, and that would give us 2. So the other thing in order to get a radical in simplified form is to make sure that your answer does not have a fraction under the radical sign. For instance, the square root of 1/2. We would need to simplify this further to get our final answer. And then the other term of simplified form for radicals is to make sure that you don't have any radicals in the denominator of a fraction. So for instance, we have, let's say, 5 over square root of 2. This expression here is not in simplified form because we have a radical in the denominator. So let's try a few examples. Okay, for our first problem, we're going to simplify the square root of 8. So using our product property for radicals, our first property, we can rewrite the square root of 8 as the square root of its factors. So we have the square root of 4 times 2 is 8, so square root of 4, and this is the same as if we were to multiply by the square root of 2. So looking here, we know that 4 is a perfect square, so we can take the square root of that easily, and that's 2, so we can rewrite this as 2 times the square root of 2, because this is in its simplest form. We can't reduce that anymore. So our final answer for this first problem is 2 times the square root of 2. So the second problem is the cube root of 54. Now let's rewrite this as the cube root of 27 times the cube root of 2, because we know that 27 times 2 is 54, so these are a couple factors. And we also know that 27 is a perfect cube, because we can do 3 times 3 times 3 to get 27. So we can simplify this further and make the cube root of 27 3. And now the cube root of 2 is as simple as we can get there, so we'll just write that in our answer here. So simplifying the cube root of 54 gives us 3 times the cube root of 2. The third problem here says the square root of 18x cubed, so we need to simplify that. So let's see what we get. If we were to expand this expression underneath our radical sign, so we know that 18, 2 factors for that are 2 and 9. So we can write 9 times 2 under our square root sign. We also know that we can write x to the third as x squared times x, because when you multiply x squared and x, you get x to the third. So if you're looking here, we can see 2 perfect squares underneath our radical sign. We have 9 is a perfect square, and x squared is also a perfect square. So we can rewrite this expression here as the square root of 9x squared times the square root of 2 and x. And then looking here, so we can simplify 9x squared. When we take the square root of that, we can simplify it to 3 and x, because the square root of 9 is 3 and the square root of x squared is x. And then the rest of our expression here is the square root of 2x. So here is our answer for our third problem. When we simplify the square root of 18x to the third, we get 3x times the square root of 2x. So our last problem here, we have the cube root of 40x to the fourth and y to the seventh. So I'll rewrite this as the cube root, and let's figure out some factors here. So 40 is the same as writing 8 times 5. So we'll write that in here. And then x to the fourth is the same as writing x to the third times x. Now remember, we're dealing with a cube root here, so that's why I'm thinking in perfect cubes. I'm trying to find perfect cubes in my factors. And then y to the seventh is the same as writing y to the sixth times y. All in here. And then we can look underneath this radical sign at our radicand and we can find some perfect cubes. So we have 8 as a perfect cube, we have x to the third as a perfect cube, and we have y to the sixth as a perfect cube, because y squared times y squared times y squared gives us y to the sixth. So let's go ahead and then simplify this. We're going to use our first property for radicals, the product property, and we can put our perfect cubes under the cube root sign and what's left under another cube root sign as we did previously, but I'm just going to kind of do that in my head to streamline this process. And take the cube root of 8, which is 2, the cube root of x to the third, which is x, and the cube root of y to the sixth, which is y squared. And then this is what we have left under our cube root sign. We have 5 here, we have x, and we have y. So 5x, y. Don't need that long. And then here is our final answer. So when we simplify the cube root of 40, x to the fourth, y to the seventh, we get 2x y squared times the cube root of 5xy. Let's move on. We're going to try a couple problems that work with the quotient property. Okay, remember that the quotient property states that you can take the nth root of a quotient and write that as the same as taking the quotient of the nth roots. So for our first problem, we have the square root of 20 over 16. So we can write this, we have the nth root of a quotient, we can write this as saying we are taking the square root of 20 over the square root of 16. So an nth root of a quotient becomes a quotient of the nth roots. So now let's simplify this further. Looking at the denominator here, normally we don't want a square root or any type of radical in our denominator, and 16 is a perfect square, so we can simplify that denominator very easily. We have the square root of 20 over square root of 16 is 4. Okay, so now looking at this, if we look at 20, we want to think about the factors for 20, and we can see that we can rewrite this as if we were saying 4 times 5, and we're taking the square root of 4 times 5. And 4 is a perfect square. So if this is still all over 4, then we can simplify the top here. Square root of 4 is 2, and that's times the square root of 5, because we can't simplify that any further, and that's over 4. And then our final step is to divide out our common factors. So we have 2 over 4 becomes 1 over 2. So 1 times the square root of 5, and our numerator is just the square root of 5, and we're left with that over 2. So if we're simplifying the square root of 20/16, we get the square root of 5 over 2. Let's try another one. Here we have in our numerator 4 plus the square root of 12, and that's all over 2. So let's look at this radical to start. We can rewrite this as if we were saying the square root of 4 times 3. And all of this is still over 2. Again, just as we did above, the square root of 4, 4 is a perfect square, so we can take that as being 2. Let's rewrite this, carrying over everything still that we haven't worked with yet. 4 plus the square root of 4 is 2, and still underneath our radical is a 3, because that's in its simplest form here. That whole expression is under 2. Now we need to divide out our common factors, so we have 4 divided by 2 is 2, and then 2 divided by 2 is 1, so it's just 1 times the square root of 3, which I'll just write as the square root of 3. So our answer for our second problem here, if we were to simplify 4 plus the square root of 12 all over 2, we'd get 2 plus the square root of 3. One of the conditions for getting radicals in simplified form is to make sure that if you have a fraction, you don't have any radicals in the denominator of that fraction. And in order to get rid of those radicals in the denominators, we need to rationalize the denominator. Now that's just a fancy way of saying getting rid of those radicals in the bottom part of your fraction. So let's try a few examples. The first one, we have the square root of 1/2. So using our quotient property, we can rewrite this as the square root of 1 over the square root of 2. Now we have a fraction here with a radical in the denominator, so we need to rationalize it, which means that we need to find a perfect square in order to get rid of the radical sign and just end up with a whole number here. So we can multiply the top part of our fraction and the bottom part of our fraction by the square root of 2. Because when you multiply the square root of 2 by itself, you end up with just the radicand, which is 2. So this simplifies to the square root of 1 is 1 times the square root of 2. So we'll write the square root of 2 at the top in our numerator. In our denominator, the square root of 2 times the square root of 2 is 2. So here's our answer for our first problem. When we simplify the square root of 1/2, we get the square root of 2 over 2. The next problem says 4 over the cube root of 2. Now we're dealing with a cube root instead of a square root, so we need to look for perfect cubes. So we can multiply this, the top and the bottom, by the same number. And if you look, we just have 1, 2 here underneath this radical sign here. So we need to multiply it to get a perfect cube, and we need to multiply it by 2 squared, because then we have 2 times 2 times 2, which is a perfect cube. So then we'll multiply our numerator by the same thing, 2 squared, and then multiply it out and simplify. So in the top we have 4 times the cube root of 2 squared. And that's over the cube root times 2 times the cube root, the cube root of 2 times the cube root of 2 squared gives us 2. And so let's simplify this, divide out common factors. 4 divided by 2 is 2, and this is the cube root of 2 squared, or otherwise written as 4. So here's our answer for this second problem here. 4 over the cube root of 2 simplifies to 2 times the cube root of 4. So our last problem here, we have 1 over the cube root of 9. Going about it the same way as we just did in this problem, we're looking for a perfect cube because we have a cube root. So we could rewrite this as 1 over the cube root of 3 squared, because 3 squared equals 9. So we have 2 factors of 3 here. We need 1 more in order to make it a perfect cube. So let's multiply the top and the bottom by the cube root of 3. That's 1 more 3, 1 more factor to add to this, or to multiply to this, in order to make it a perfect cube underneath that radical sign. So we're multiplying the top by the same thing. And then when we simplify this out, we have 1 times the cube root of 3, which is the cube root of 3. And that's all over the cube root of 3 squared times the cube root of 3 gives us 3. And here's our answer for this last problem. 1 over the cube root of 9 simplifies to the cube root of 3 over 3. So now let's move on and we're going to work with some operations that use radicals. When adding or subtracting radicals, you're looking for similar radicals. And those are radicals that have the same index and the same radicand. For instance, we have 2 times the cube root of 6, and we're comparing it to -7 times the cube root of 6. So if we look at these two radical expressions, we have a 3 for an index on this first one, and we have a 3 for an index on the second one, which means they're the same there. Looking at the number underneath the radical sign, which is called the radicand, we have a 6 and a 6. So these two radical expressions are similar. Looking at the next comparison, 4 times the square root of 5 and 2 times the cube root of 5. Now the radicands are the same, however the radical expressions have 2 different indices. So we have a 2 here for our square root for the index, and then the index on this second expression here is a 3 for our cube root. So since those are different, these ones are not similar. And lastly, for the 3 times the square root of 2 compared to 8 times the square root of 3, we have an index of 2 on this first radical expression and an index of 2 on the second, which means they are the same there. However, the radicands are different, the square root of 2 versus the square root of 3. And so those two expressions are also not similar. So using this knowledge here, let's work these next two problems. We have 5 times the cube root of 10 minus 4 times the cube root of 10. So we look and we have two radical expressions here that have the same index and the same radicand. So we can apply our distributive property and rewrite this as 5 minus 4. So we're pulling out these numbers here, and that's going to be times the cube root of 10, since these are similar radicals. And so you simplify that. 5 minus 4 is 1, so our final answer is the cube root of 10. There. So the second one, at first glance, we don't have similar radicals here. We've got the square root of 20 minus the square root of 80 plus the square root of 45. But let's simplify each radical expression individually and then see if we can combine them. So the square root of 20, we can rewrite that as the square root of 4 times the square root of 5. And then we subtract the square root of 80, which we can rewrite as the square root of 16 times the square root of 5. And then the square root of 45, we can rewrite as the square root of 9 times 5. So then we look at these factors under the radical signs and we find some perfect squares. So the square root of 4 here we can write as 2, and then the remaining factor under the square root sign is 5. And then we subtract square root of 16 times 5, we've got a perfect square in 16, so the square root of 16 is 4. That's times the square root of 5. And then we're adding our final expression here. The square root of 9 is a perfect square, 9 there, so we have the square root of 9 equals 3. And then finish it up by multiplying the square root of 5. So now, if you look at our terms in this expression here, we have similar radicals because we have the same index on each one, which is 2, and then the same radicand, which is 5. So we can combine this. Let's use our distributive property. We have 2 minus 4 plus 3, and that's all times the square root of 5. Simplifying that, 2 minus 4 is -2 plus 3 is +1. So it's 1 times the square root of 5, otherwise known as just the square root of 5. So there's our final answer for this problem here. The square root of 20 minus the square root of 80 plus the square root of 45 simplifies down to the square root of 5. The last thing I'd like to discuss is how to multiply and divide radicals. So our first problem, it says multiply 2 times the square root of 3 times 5 times the square root of 7. So we can rewrite this as 2 times 5 times the square root of 3 times the square root of 7. And then simplify. 2 times 5 is 10. And then using our product property for radicals, this square root of 3 times the square root of 7, we can rewrite that as the square root of 3 times 7. And then that simplifies to 10 times the square root of 3 times 7 is 21, which is our answer. So to multiply two products together, including radicals, is essentially the same as if we were multiplying two polynomials together. So let's move on and let's try a division problem. So here, we spoke earlier about rationalizing the denominator. So we need to get rid of the radical that's in the denominator of this fraction. To do that, we need to multiply the top and the bottom of this fraction by the same number, and we're going to multiply by a conjugate. So that word, conjugate, is an important one to remember. And the conjugate of this expression here is the square root of 5 minus 1. So this expression, these two expressions are conjugates of each other. So we're going to multiply the bottom of our fraction by the conjugate and multiply the top of our fraction by the same thing. Okay, so now let's simplify this. We have a square root of 5. We're going to combine that. That's times the square root of 5 minus 1. And that's over the square root of 5 plus 1, this quantity here, times its conjugate, the square root of 5 minus 1, is essentially the difference of two squares. So we can write this as the square root of 5 squared minus 1 squared. And then we simplify. So I'm going to move it down here. We use our distributive property. We've got the square root of 5 times the square root of 5. And then the square root of 5 times negative 1. Which you can write this then as the square root of 5 times the square root of 5 minus this whole quantity. Square root of 5 times 1. And that's all over our difference of squares. So the square root of 5 squared gives us 5. And then 1 squared is 1. So our denominator is 5 minus 1. So we have rationalized our denominator. We've gotten rid of our radicals. Let's just simplify what we have left to find our answer. So the square root of 5 times the square root of 5 gives the square root of 25, which is just 5. And then we subtract the square root of 5 times 1, which is the square root of 5. And that's all over 5 minus 1, which is 4. So this is our answer. It's okay that we have a radical in the numerator. That's simplified form for radicals. We just didn't want any radicals in our denominator. So our answer for dividing this fraction here is 5 minus the square root of 5 all over 4.